All right. 1960 and 1965, there was the Pound-Rebka and Pound-Snider experiments that conducted respectively. What they were doing here is they were looking for a frequency shift in a photon that was emitted from the top of a tower, and then it would hit this detector here at the bottom, and this detector would only accept a certain frequency shift um, before it would even register anything, right? So they had their predictions for how much the photon would shift due to an interaction with Earth's gravitational field in accordance with Einstein's relativistic theory. And they also had a prediction for classical mechanics in such that there would be a frequency shift due to relative motion. And basically what they're saying in there is that it would appear as if the speed of light changes c plus v or c minus v when it's going up or down the tower. So when it's falling towards the ground, it's plus v. When it's going up the tower, it's going minus v. So it's going to be. So they're saying we're trying to figure out, is the speed of light changing? Is it going faster or slower, or is Earth's gravitational field the mechanism for causing the frequency shift in the wavelength and frequency, or is it the relative motion? Right? Is it actually gaining speed, like in the Galilean sense, where it's c plus v, or is it in the relativistic sense, where you apply length contraction or the gamma factor to the frequency, right? So what were the conclusions of the experiment? So Pound-Rebka here, 1960, yeah, 1960. They were inconclusive in their results. They make no distinction between relativistic effects and the classical effects. So what they're saying here is that they have no idea if the photon, so-called, is if it's accelerating at 8.9 meters per second squared and it's gaining that acceleration to the speed of light, which is causing a frequency shift proportional to that, or is it interacting with the gravitational field and the speed of light is the same, and it's just the gravitational field is shifting, shortening, and lengthening the wavelength and frequency proportionally to compensate, right? So that's they couldn't figure it out in 1960, so they did another experiment in 1965, same thing, and then this time they used a what was it? They used a gamma radiation instead of a photon, right? So literal same exact experiment, and they reached the same conclusion in the first one. And I have the slides, or I have it sectioned out or whatever on this other presentation. So I'll show you what they're saying here. So it is not our purpose here to enter the many-sided discussion of the relationship between the effect under study and general relativity or energy conservation. It should be noted here that strictly no relativistic concepts are involved in the description of the effects of the apparent or description are involved in the description of the effect as an apparent weight of a photon is suggestive. So remember back to their first paper, they were saying, hey, the apparent weight of a photon, we really don't know, right? So they're saying, they're like further, this is their new paper, 1965. They're further standing by that. And it says the velocity difference predicted is identical to that of which a material object would acquire in a free fall time equal to the time of the flight. So there's a downward acceleration to that, and that's causing the frequency shift. If there wasn't, there wouldn't be a frequency shift, right? So a priori, so this is where they were trying to say maybe the Earth's rotation was contributing to that, but that's not it. So the let's see, what was the other one? Okay, yeah. So the view that the local timescale depends on the gravitational potential appears to require a more coherent source for confirmation. The present experiment is unable to distinguish between frequency changes and velocity changes. For example, it appears as if the experimental comparison by clock at different potentials would make a useful complementary contribution to the overall status of this theory. And then that's where you get into the Heffel and Keating with the atomic clocks. That didn't really go the way that they needed to either. But this experiment here was supposed to supplement the relativistic claim that gravitational fields are real and that there's an interaction between a photon um, and the gravitational field such that it causes gravitational redshift, right? So this is an inconclusive experiment. The only thing that they've found here is that the speed of light goes faster going down and goes slower going up. So there's a preferred direction down and there's a preferred direction up, in the same respect that there's a preferred direction going east. The speed of light is faster going east, and there's slower going west. So that's what they were able to to determine from that. So, and the reason that they don't talk about it in the sense that I just did is because C plus V is the Galilean law of velocity addition. So you wouldn't do that for light. You wouldn't do that for C, right? Because of relativity now. So for C, you apply the gamma correction. You don't apply C plus V. So that's why they don't really talk about it in that regard. But that's what they were saying, that the speed of light is either going faster down and slower up, or the gravitational field of the Earth is changing the frequency through some interaction that can't be that can't be described, right? Other than mathematically. So that's the mechanism for the interaction. That's the experiment that shows that there is a preferred downward direction for the propagation of light.